Hello and welcome back. In this video, we're going to take a look at the different concentration units that we use or we're going to use this semester and when we're talking about solutions. So on the board, I have them all written out for us. Molarity is a unit that you have already seen and have used in 1411 or first semester of general chemistry. Molarity is symbolized by capital M and is defined as moles of solute per liter of solution. All right, percent can be in different types of percent, so I've just summarized them by writing it all here. If it's percent by mass, then it's grams of solute per gram of solution times 100. Keep in mind percent is part per total. So if it's percent by mass, part and total are both in grams. Grams solute per gram of solution times 100. If it is percent by volume, if the solute and the solvent are both liquids, then we use percent by volume, and it would be milliliter solute per milliliter of solution times 100. Now, if it just says percent and it doesn't specify by mass or by volume, oftentimes it's kind of a mix of the two. It will be grams of solute per milliliter of solution times 100. Okay, another concentration unit that is going to be very useful for us in a later video and in your laboratory is molality. Now let's go back and take a look at molarity, which is something that you have used a lot in the lab. Moles are just an amount, right? But liters, volume, is temperature sensitive. If you change the temperature, the substance is going to, if you increase temperature, then the molecules are moving faster, they're going to expand. The volume is temperature dependent. Now, molality is a concentration unit that is temperature independent. It is symbolized by lowercase m. When you read or when you see M, it is called, you read it as molal, just like the capital M is read as molar, right? And the next ones, it'll be normal. Okay, so now we have them all stated. All right, so for molality, the definition, it's very different. Moles of solute, it's not per solution now, it is per kilogram of just the solvent. This is a distinguishing factor of molality relative to the other definitions that we had. This is total solution, and this is the total amount of moles. It's for all the substances in solution. This is the only concentration unit that deals with only the solvent in the denominator. Okay, the next one is a concentration unit that is not as commonly seen anymore, but it's very useful, and that is normality, symbolized by capital N. And when you see capital M, you say normal, just like capital M is molar. Okay, and normality and molarity are very closely related. Normality is defined as the equivalence of solute per liter of solution. Now look at the definition here and for molarity, and the only difference is here we're dealing with moles of solute, here we're dealing with equivalents. So what exactly is an equivalent? Well, it depends on the type of substance. An equivalent, I have a little scheme over here for you, or a list. If you're dealing with an acid, a mole of hydrogen ions is 1 equivalent. A mole of hydroxide ions for a base is 1 equivalent. If you're dealing with a redox reaction, a mole of electrons transferred is an equivalent, and we'll use this relationship when we get to the electrochemistry unit at the end of our semester. And if you're dealing with a substance that's not an acid or a base or a redox type reaction, just look at the mole of charge on the cation. Each mole of charge is 1 equivalent. To get to molarity, to get to normality, start with molarity, get the concentration in molar, and then multiply by a factor going for each mole of substance how many moles of the active ingredient as listed here. Okay, And the last concentration unit that we will be dealing with is called mole fraction. This is a little bit similar to the percent. It's part per total, but it does not get multiplied by 100. It remains as a fraction, and it is a part per total moles. So if you're dealing with component A, whether that's a solute or a solvent, it doesn't matter. So let's say it's the solute, okay? You're going to deal with, calculate the moles of solute, calculate the moles of solvent, and then you will add the 2 moles, the total number of moles in the denominator, and you have moles of solute divided by moles of solute plus the moles of solvent, the total moles that are present. Okay, so that's an overview of all of the different units. Now let me give you a problem to work so that you can practice these. Okay, so the problem is this. A solution is made by dissolving 29.25 grams of sodium chloride in enough water to make 500 milliliters of solution. The density of the solution is 1.086 grams per milliliter. Based on this information, calculate A, the percent, the concentration in percent, B, molarity, C, molality, D, let's make C normality, D, molality, and E, mole fraction of water. So if you would pause the video and work on these calculations, and then come back and we'll pick it up. We'll work these together. Okay, for percent, since I didn't specify, we can do grams of solute. So this is the solute right here. This is what's given for our solute. This is given, this is the total solution, all right? And so if we would do grams of solute, which is sodium chloride, that's given 29.25 grams per, we could do milliliters, 500 milliliters of solution times 100. Okay, for molarity, we need to determine the, this is moles of solute per liter of solution. So we're going to take the 29.25 grams of sodium chloride, put this back up later, times, we have to convert this to moles. We get rid of grams and get to moles. 1 mole of sodium chloride weighs 58.5 grams. So this now gets us to moles of sodium chloride, and we need to divide by the liters of solution. We have 500 milliliters, and if we move our decimal over 3 places, that gives us liter of solution. Now, normality, as I mentioned previously, start with your molarity, and the molarity value should be calculated as 1.00 molar. 3 sig figs because of the volume. And let me get rid of the capital M and write the units. This is moles of sodium chloride per liter of solution. We need to get to equivalence. So let's take a look at our substance, our solute. Well, this is not an acid. This is not a base. This is not a redox reaction. It's just a compound in solution. So we are going to determine the equivalence based on the charge on our cation. So for each mole, 1 mole of sodium chloride is 1 equivalent. Because there's a +1, there's 1 +1 or 1 mole of charge on the cation. So the normality is the same as the molarity here. And we would say 1.00 normal. Okay, lastly, let's do, well, it's not lastly because we have to do mole fraction, but let's get back to the information that we have here so that we can determine the molality of the solution. So starting off, molality is the moles of sodium chloride, which we already had before, divided by kilograms of water. Moles of sodium chloride, we're given the grams, we can get to moles, and we did it in the previous calculation, right? We know that we have 1 mole, 1.00 moles of sodium chloride that we calculated previously. How are we going to get kilograms of just water? Well, we know the volume of the solution, which is solute plus solvent. Both are accounted for there. We have a density that can take us from milliliters of solution to grams of solution. And remember that solution is solute plus solvent. Okay, so let's figure out the mass of our solution. We have 500 milliliters, this is all solution, times 1.086 grams of solution per milliliter of solution. Our milliliters of solution cancel, and this gives us grams of solution, is equal to grams of solute, which is given, 29.25 grams, plus unknown grams of water. Let me write this, sodium chloride, so we know exactly what we have. Okay, so if we determine the grams of water here, then we would get kilograms, and we put the kilograms here. And let's see. Okay, so calculating this out, we have, this ends up giving us 543.000 milliliters of solution is equal to 29.25 grams of the solute sodium chloride plus unknown amount of, or grams of water. Solving for the grams of water, we subtract and we end up with 513.75 grams of water. We're almost there. We need it in kilograms. We will move our decimal over 3 places, and we have the molality is 1.00 moles of sodium chloride per 0.51375 kilograms of water. All right, so if we, let's get that, let's get an answer there. And the answer then, our molality is 1.95 molal, or we can write moles per kilogram, which are the units. Now I'm not going to erase this part to do the last calculation of mole fraction, because we're going to use these numbers here in just a moment. Now to do the last calculation of mole fraction, all right, so mole fraction, and I specified water. So let's figure out This is going to be moles of water divided by moles of water plus moles of sodium chloride. Let's determine the moles of water, 513.75 grams of water. And we convert to moles. There are 18 grams of water per 1 mole. So then we get 28.542 moles of water. Okay, so now we'll go in and plug into our definition. We have 28.542 moles of water divided by, this is the moles of water, we had 1.00 moles of sodium chloride. This is water. So the total moles is 29.542 moles. And we get the mole fraction then of water is 0.966. And we limit our answer to 3 significant figures because, remember, we use the volume of 500. That's 3 significant figures, so that's the number of sig figs that should be in our answer. Notice that there are no units, and it is a fraction. It's a decimal value. It's not a whole number yet. So it doesn't reach, it's less than 1. So it'll be a fraction of 1. We don't write it as a fraction, we write it as a decimal, but it is less than 1. All right, and that wraps up our lesson on solution concentration.